Hey guys, this is Kevin Mudashevsky, and this is the HMP shunt. So the hexose monophosphate shunt, also called the pentose phosphate pathway, is shown here. This takes place in the cytoplasm of the cell. Its purpose is to synthesize NADPH and ribose sugars when glucose 6-phosphate is abundantly available. The HMP shunt can be broken down into two distinct steps. These are the oxidative or irreversible step, or the non-oxidative or reversible step. In the irreversible oxidative phase, the first molecule of NADPH is produced by the first enzyme glucose 6-phosphate dehydrogenase. Another is produced later on. Do you guys remember what NADPH is used for in the body? NADPH can be used in reductive and anabolic reactions such as glutathione reduction in red blood cells, as well as cholesterol synthesis in the liver. If the cell already has plenty of NADPH, this pathway will actually be shut down since NADPH inhibits the rate-limiting step, which is G6PD. So in addition to the oxidative or irreversible phase, shown up here, this pathway also consists of a non-oxidative or reversible phase. The irreversible steps created the NADPH, but the reversible non-oxidative steps will create ribose 5-phosphate derivatives using the phosphate isomerase and transketolases. These ribose derivatives can be used elsewhere in the body, such as in nucleic acid synthesis. The transketolases require vitamin B1 to be used and are often used to test for B1 deficiency. Notice here how the end products of the HMP shunt feed back into the glycolysis pathway. This way the body can use the HMP shunt to make NADPH or ribose derivatives without creating much waste. Alright, time for a flash quiz. So a 2-year-old girl is born with a glucose 6-phosphate dehydrogenase deficiency. This interferes with which step in the HMP shunt? Well, this would disrupt the irreversible or oxidative phase, or the first reaction in the HMP shunt, which converts the glucose 6-phosphate into CO2, 2 NADPH, H+, and ribose 2-phosphate molecules.